Hello everyone. In this video, I'm going to talk about some of the model selection methods that we can use to find the best possible model for our research. This is the reading list. We won't be covering all of chapter 6, rather a section of that. So when you're reading the chapter, make sure to tally it with the slides so that you can get the most out of it. Now, linear models are great. We have covered that and we know how it works, why it is useful. But then the question is, why do we even care about model selection? In other words, why should we think hard about deciding on which predictors to keep in the model and which ones to throw out? Uh, we need to be careful because if we have a model with too many variables, we might end up with a problem of overfitting. This means that our model starts memorizing the, the smaller bits and pieces of the data rather than actually learning the patterns of the larger data. And that is not good. We also care about interpretability. I mean, if you have a model that is very complex, that will be hard to interpret and present rather than model that is much more simpler. And there's always this trade-off between variance and bias. Complex models might catch more patterns, but also can be super sensitive to random noise. Simpler models might miss some of that stuff, but tends to be more stable. And this becomes very important when you have a lot of predictors in your model, especially situations where the number of predictors is much larger than the number of observations. So you need to be really picky about which variables to include. Check out this graph. It shows exactly why model selection is tricky. The two lines over here is one, the blue line is the training error, and we can see that as you increase the model complexity, training error goes down. But the opposite seems to be happening for the testing error. So as we make more and more complex models, the testing error does seem to go down a little bit, but then eventually it starts to grow. It starts to become larger and larger. And this is a classic sign of overfitting. The model is so complex that it is learning the noise in your training data. And now the question is, where is the sweet spot? To understand that, we will cover three approaches to model selection. First up is subset selection, which is basically deciding which predictors to keep and which ones to throw out. There's best subset selection, forward stepwise, and backward stepwise methods. We will dive into each of these in a minute. The second approach is using shrinkage methods. Here you keep all your predictors but kind of dial down their impact. Methods like ridge and lasso regression shrink the coefficients of less important variables, and lasso can even shrink them all the way to zero. The third approach is the dimension reduction. This is like taking your original variables and creating a new super variable that captures most of the information. Principal component analysis, or PCA in short, is a classic example of that. In this video and in this module, we will be focusing on subset selection. The first step is best subset selection, and it is exactly what it sounds like. We are looking for the best subset of predictors. It is the most thorough approach, but is also the most computationally exhaustive. Here is how it works. We literally try every possible combination of predictors and pick the winner. So if you have p number of predictors, you will end up with 2 to the power p possible models. And that gets big very fast. For each model size, we find the best model with that many predictors. To give you a sense of scale, with just 10 predictors, we need to check 1,024 different models. That is a lot of work, and that is why we sometimes need to look for shortcuts, which I will talk about next. Let me walk you through how the algorithm of best subset selection works. We start with a super simple model, a model that has no predictors but just the intercept. That is our baseline. Then, for each possible number of predictors from 1 to p, we fit all possible models with exactly that many predictors. For each size, we select the champion model, usually the one with the lowest lowest RSS or the highest adjusted R square. Finally, we have these champion models of different sizes compete against each other using a criteria that we will talk about later. The big downside, as I just mentioned, it gets computationally expensive really fast, really soon, if you have a lot of predictors. And sometimes it's not practical to try every single computation combination as well. So that's why we have some alternatives that help us avoid this problem. The first is the forward stepwise selection, which is like a more efficient cousin of best subset selection. Instead of trying every possible combination, we take a greedy approach. We start with a no predictor situation and then add variables one by one, always picking the most helpful predictor at each step. This is way more efficient. Instead of checking 2 to the power p number of models, we only need to look at this number, which is a far less number to work with. And that is a huge difference as p gets large. The big advantage of that is that it's actually doable even when you have more predictors and observations. Plus, it tends to have less variance since we are not considering many models. But there's a catch. The catch is that since we are greedy over here at each step, we are always picking what looks best at that point, which means that we might miss out on a truly optimal model, and sometimes the best combination isn't found by adding one variable at a time. So in other words, the way this works is that once a variable has been selected in a, say, 2-variable model, that variable will always stay in all higher number of predictors model. So that is how it works. Once it's in, it will always stay in for the rest of the iterations. Whereas best subset selection can potentially look at other combinations as well. Backward stepwise selection kind of flips the script. We start with everything in it and then remove variables one by one. We begin with the full model that includes all predictors and then iteratively kick out the least helpful predictor at each step. Like forward selection, it's much more efficient than checking every possible model. One cool thing about backward selection is that it can catch effects that only show up when certain variables work together. Since we start with all variables, we see these interactions before removing anything. But there's a downside as well. First, we cannot use this when p is greater than n, because you can't even fit the initial full model. Second, just like forward selection, this greedy approach might not find the truly optimal model. And to illustrate that, here's an example. So this table shows what variables get selected for models of different sizes. This is just an example. So when we're looking for a model with just one variable, both best subset and forward stepwise selection method picks rating. With 2 variables, they both choose rating and income. With 3 variables, they still agree, rating, income, and student. But check out what happens with 4 variables. Now there's a disagreement. Best subset selection goes with cards, income, student, and limit, while forward stepwise picks rating, income, student, and limit. This shows something important. These methods often give you similar results for simpler models, but can start to differ as model gets more complex. That's because they're taking different paths through the huge space of possible models. So once we have found the best model for each size, now the question is which size should we actually go with? And here are 4 helpful criteria. First is the adjusted R square. So this penalizes you for throwing in more predictors. It asks the question, is this extra complexity really worth it? And if yes, you keep it in, else you throw it out. And higher values are better here. Then there is something called the Mallows CP measure, which estimates prediction error. Lower values suggest better models. AIC or Akaike information criteria is similar to CP and is super common for maximum likelihood models. Again, lower is better. BIC or Bayesian information criteria is like AIC's stricter cousin. It penalizes the complexity but even more harshly, and this tends to push you towards simpler models. And these methods just help us find that golden balance. A model complex enough to capture the real patterns, but simple enough to avoid chasing noise. And that is the ultimate goal of model selection. So that is it. I hope this was useful. Please let me know if you have any questions. Thank you.